Right, so hi everybody. Today what we're going to be doing is a lab on diffraction. So just to remind you, diffraction is something that affects all types of waves, whether they be light waves, sound waves, or waves on the surface of a body of water. And diffraction is this effect where when you send a wave through an opening, the wave tends to spread out after going through the opening. And in a similar way, if you put a barrier in front of a wave, the wave tends to also spread out after going around the barrier. Now, diffraction is a really important effect because, among other things, it really sets a limit on how well we can resolve the fine features of something using an optical instrument like a microscope or a telescope. So let's take the example of a point source of light. Okay? So imagine light waves from this point source are going through your eye. They're entering your eye through the pupil. So the pupil is a little opening in your eye which has a finite size, of course. And after this point source of light goes through your eyes, the waves are going to spread out. So what was once a little point of light now looks a little bit more blurry. Okay, and in a similar way, if you looked at this point source of light with a huge telescope, those light waves would be going through the aperture of that telescope, which again is a finite sized opening, and they would spread out after going through there. And in a similar way, that would blur the light. So no matter what you're using as your optical instrument, there's going to be diffraction when the light enters that instrument, and that diffraction is going to have the effect of blurring the light. So that means you can't really see things or image things with infinite resolution, right? There's always some kind of limit to how well you can resolve the fine features of something when you look at it with an optical instrument. So with that said, our experiment today is going to be divided up into 3 parts. And the first part is going to involve sending a laser beam through a narrow slit. That's the diffraction pattern we're going to look at first. All right, so here's the experimental setup. On the very far right side of the track, what we have is a laser, and the wavelength of this laser is 635 nanometers. So the wavelength we'll be using throughout the experiment is going to be 635 nanometers. Next to that, we have a slit assembly. So this has various types of slits that we can send the laser beam through. And then if we follow along the track to the other side, what we have is a light sensor. So this can tell us the intensity of the light that's hitting it, but not only that, we can move the sensor around so it can tell us the position where we're reading a certain light intensity. So if we go to the computer monitor, this is our interface where we actually read the data off. And what we'll be doing is looking at how the intensity of the light is changing with position. And we'll make a graph of that using the computer interface. Okay, the last thing to note here is there's a distance that we need to take note of, which is the distance between the sensor and the slits along the track. Okay, so the sensor is placed at the 20 centimeter mark, and the slits are exactly at the 95 centimeter mark. So the distance between them is 75 centimeters. So 75 centimeters is the distance between the sensor and the slits. Let's take a look at our diffraction pattern with the room lights off so you can see it a little bit better. And what you're looking at here is the diffraction pattern that is created when we send the laser beam through a 0.04 millimeter slit. So the width of the slit, in other words, is 0.04 millimeters. So that's the diffraction pattern that's produced, and as you can see, it consists of bright spots, and in between those bright spots, some dark spots. And the reason for that is basically at certain points you have constructive interference, where you see the bright spots, and where you see the dark spots, you have destructive interference. So what we're going to do is measure this diffraction pattern by putting the sensor all the way at one side, and then just gradually pushing it to the other side. And the whole time we're sweeping across that diffraction pattern with the sensor. Okay, and then once we reach the other side of the track, we've pretty much covered the entire pattern, and then we can look at what it looks like when we plot it out. Okay, so if we plot out the data on an intensity versus position graph, so in other words, intensity is on the vertical axis right here, and then position of the sensor is on the horizontal axis right here. And you can very clearly see the diffraction pattern with that central peak shown right here. So what we want to do is measure how wide that central peak is by starting at the very center of the peak right here. So just click on the central peak and then drag all the way to the first minimum, which is right about here. And so the distance between that central peak and the first minimum is 13.01 millimeters. So 13.01 millimeters. Okay, so what I've done is I've changed the slit. Now we're sending the laser beam through a 0.08 millimeter slit. So the width of the slit, in other words, is now 0.08 millimeters. And this is the diffraction pattern we're getting. Notice how it's not quite as wide as before. It's a little tighter. We're going to do the same thing as before. To measure the pattern, we're going to start with the sensor at one end and then push the sensor across to sweep over the entire diffraction pattern. So we can see how the intensity changes with position. And so this is what it looks like when we plot the diffraction pattern for the 0.08 millimeter slit. What we're going to do is, like before, measure the distance from the central peak to the first minimum. And so what we're getting for that distance is 6.49 millimeters. So 6.49 millimeters. Okay, so I've changed the slit once again, and now the width of the slit is 0.16 millimeters. So we're with the wider slit, now we're getting a much more narrow diffraction pattern. And just like before, we're going to sweep across the diffraction pattern with the sensor so that we can see how the intensity changes with position. Okay, so here is the diffraction pattern when we're using the 0.16 millimeter slit. And so just like before, what we're interested in is the distance from the center of the pattern to the first minimum. And so that is 3.00 millimeters on the dot. So 3.00 millimeters. Okay. So for this next part of the experiment, we're not going to be using slits to create a diffraction pattern. Instead, we're going to use a piece of hair, which I've taped to this glass slide here. So in other words, we're going to shine the laser beam right on the piece of hair. As that light goes around this barrier, it's going to create a diffraction pattern. And we can actually use that diffraction pattern to figure out the width of this hair, which is not something we'd be able to measure with a ruler or anything like that. Okay, so this is our new setup. Notice how I've replaced the slit screen with the glass slide that has a piece of hair taped to it on this side of the track. And if we look at the other side of the track where the diffraction pattern is being projected, this is what it looks like. So, like I said, when you take a source of light like a laser beam and you put a barrier in front of it, it will diffract around that barrier. So this is what the diffraction pattern looks like. So we're using the same exact laser as before. The wavelength is 635 nanometers, and the distance between the piece of hair and the sensor is 75 centimeters, just like before. Okay, so using the exact same method that we used before, we're going to measure the diffraction pattern, again by starting with the sensor all the way at one end, and then slowly pushing it to the other end. All this time we're sweeping across the diffraction pattern and seeing how the intensity is changing with position. So this is the diffraction pattern that we get when we put a barrier, that is the piece of hair, in front of the laser beam. Now this doesn't look nearly as clean or pretty as the ones we had before, but we can still identify that this is the central peak, and then we have a minimum on either side of that peak. And all we really need to do is measure that distance between the center of the peak and the first minimum. So here we go. Just Click on the center of the peak and then drag that all the way to where you see the first minimum, which is about here. And that distance is 0.64 millimeters. So 0.64 millimeters is the distance from the central peak to the first minimum when we have the hair creating the diffraction pattern. Okay, so we've replaced the slide with the piece of hair on it with the slit apparatus back on the track. And right now it's in a double slit setting, so there are two slits. The separation between them is 0.25 millimeters, but the width of each slit is 0.08 millimeters. So that's what we have right now. And if we look at the interference pattern that's created, it's right here. And we're going to measure it in the same exact way that we've been doing throughout this lab. Just sort of sweep the sensor across the pattern and measure the intensity at each point. Okay, so this is the graph of the interference pattern that we just measured. Intensity versus position, just like before. We just want to take a qualitative look at this graph. We're not actually going to measure anything off of it, but what I want to point out is that we have the central maximum right here, the highest peak in intensity, and then on either side of that, left or right, we have the n equals 1 interference maximum, and then on either side of that we have the n equals 2 maximum. But notice the n equals 3 maximum on either side seems to be missing. You'd expect to see a peak right there, but you don't. So part of the analysis that you're going to do is to try to figure out why the n equals 3 maximum is missing from this interference pattern. All right, so that's it for the experiment. As usual, there is a worksheet to accompany the video here, which explains the different analysis you're supposed to do using the data we collected. And so that's it. I'll see you in the next lab video. Until then, be safe and be healthy out there. See ya.